My name is Tucker Rae-Grant, and I'm presenting ExCell, High Expansion Ratio Moisture Responsive Wooden Actuators for DIY Shape-Changing and Deployable Structures. I conducted this research along with my co-authors Shuhong Wang and Lining Yao in the Morphing Matter Lab at Carnegie Mellon University's Human-Computer Interaction Institute. In HCI, architecture, engineering, and robotics, there has been sustained interest in physical systems that can undergo radical, continuous changes in shape in response to simple input. In some cases, this morphing ability allows us to incorporate autonomous functionalities into the design of otherwise unpowered materials. In other cases, shape changes harness to revolutionize the built environment, allowing for previously impossible to fabricate forms that are lofted from a flat shape into surfaces with compound curvature while only applying forces in strategic places. Many of the existing systems are enabled by bespoke computational models, precision fabrication tools, and engineering materials. While these research domains remain rich, inspiring territories, the barriers to entry for designing and fabricating shape-changing and deployable structures are high for non-experts. Some previous research has tried to address this by creating design tools that handle the complex work of mechanism design and collision avoidance automatically, or by creating a library of proven building blocks that can be assembled into more complex configurations. We decided to complement existing research by creating a shape-changing actuator focused on manual prototyping that's easy to make, easy to use, and easy to understand. Equally as important, it's biodegradable and its shape change is triggered by water, so it's appropriate for ecological applications. We present ExCell, short for expanding cellulose. Building off of the method developed by Luo et al. For creating coiling actuators out of wood, we chain alternating bending actuators together in one piece of accordion folded wood to create a linear actuator. It incorporates tab and slot connectors that make it simple to combine ExCell units with each other and with other materials to create complex modular expanding systems. In contrast to many mechanical deployable structures that bind up globally if one joint is out of place or if a member encounters an obstacle, ExCell actuators all expand independently, so as a system, it's tolerant of low precision application and of encountering unexpected conditions during deployment. In our paper, we detail the iterative process behind our design and elaborate on the geometric, material, and process parameters that affect morphing wooden systems. We found that we needed to balance multiple dependent parameters, and we believe that our findings will be helpful for future researchers developing their own shape-changing wooden systems. Let's take a look at the basic building block of ExCell, a thin piece of wood that can bend. Even though wood is ubiquitous and has been used throughout human history, recently, researchers have been taking advantage of its unique qualities to push its uses in new directions. From changing its material properties to make it ultra-strong, bendable, or transparent, to using it for energy storage and the creation of biodegradable transistors, much of this research leverages the hierarchical microstructure of wood. This microstructure makes wood highly anisotropic, meaning its properties differ depending on the material's orientation, while still being highly predictable along wood's three axes. These axes, longitudinal, radial, and tangential, correspond with the way that wood grain develops as a tree grows. For our purposes, we're mostly interested in the stiffness and cohesion of wood fibers along different axes. Another characteristic of wood is that it expands and contracts as it absorbs and releases water. If we mold a bend into a piece of wood, allow it to dry, and rehydrate it, the bend will open back up. When it dries, it will reclose. It won't go all the way back to its molded state, but I'll talk more about that later. While this mechanism has not been fully characterized, our understanding is that the bending process creates a gradient across the wood with compressed cells on the interior of the bend and stretched cells on the exterior. The compressed cells swell as they absorb water, pushing the bend open. We experimented with several different species and cuts of wood and found that flat sawn veneer from maple trees provided the best results. We chose maple because it's a widely available domestically grown species. It has relatively high stiffness, and its tight, consistent grain resists splintering better than the other species that we tried. This choice allowed us to cut larger numbers of parallel blanks without needing to carefully select areas with specific grain patterns, which is a problem with oak, which has open pores that splinter when you try to mold across them. We go into more detail about why we chose flat sawn veneer over other options in the paper, but here I'll just say that flat sawn veneer splinters significantly less when it's molded. One of our design goals was to achieve dramatic expansion, so we analyzed the geometry to determine which factors would have the greatest effect on molded length, which we want to minimize, and on expanded length, which we want to maximize. Because wood veneer is available in a limited range of thicknesses, the main driver of the length in molded units is the radius of each bend. So we want to make those radii as small as we can. In expanded units, the actuation angle of each bend and the length of the arms both play a determining role, so we want actuators that open up as much as possible with arms that are as long as is reasonable. And I'll just say here, we didn't really do a lot of tests with different arm lengths. We found that when they got sort of more than twice the width of the actuator, we ended up with something that functioned as a very soft spring when it was expanded. So we ended up just designing it to have a relatively square aspect ratio, which we found was very easy to handle during assembly. So in order to maximize expansion, we needed to understand how the molding radius affected the actuation angle. So we created a series of test actuators with different radii by molding them around 3D printed blanks. And then we triggered them and measured the angle that they opened up to. While we didn't find a clear trend, we did see that radii between 0.25 millimeters and 0.5 millimeters opened up the most. And because we simultaneously wanted to maximize actuation and minimize the radius, that range seemed good to us. We suspect that if there's better performance in this range, it's because this is sort of like a sweet spot where we're maximizing the compression of the cells on the interior of the bend while not creating such a strong gradient that we're splintering cells on the exterior of the bend. This finding created a small dilemma. How could we create alternating bends with consistent radii in relatively small pieces of wood? We experimented with different methods, including pressing the blanks between two molds, running the blanks through meshed gears, and manually forming them around interleaved 3D printed molds. This last method resulted in very consistent actuators, but involved very small prints that were prohibitively difficult to handle and align. It also required printing individual molds for each actuator in a batch, which conflicted with our environmental goals. In the end, we decided to trade greater potential actuation for reduced complexity, giving the actuators what we call a 0 millimeter bend radius, or a simple crease that did not require molds. We added laser cut notches to the blanks to guide the bends, which greatly facilitates manual folding. So how do we make these? Each ExCell actuator is composed of a laser cut piece of maple veneer that has been chemically processed, folded, and dried. Using a laser, we cut the actuator so that the longest part of the blank is aligned with the longitudinal axis of the wood. This maximizes stiffness along the actuator and helps prevent splintering during the folding process. Following Luo et al., we boil the laser cut blanks in a solution of sodium hydroxide and sodium sulfite to remove lignin, making the wood significantly more moldable. Lignin is one of the three major components of wood, and structurally it functions a lot like the polymer matrix in fiber reinforced plastics. So when you remove it, the material gets less stiff. We experimented with boiling times and found that the longer we processed the wood, the more moldable it became, but at the cost of stiffness. Our goal was to achieve consistent moldability with minimal splintering while preserving stiffness, so we found that 20 minutes of boiling worked best. After boiling, the excess reagents are rinsed off and the blanks are manually folded at the notches. The molded actuator is loosely wrapped in tissue to maintain its shape while it dries. Once dry, ExCell units are ready to be used. After submitting our paper, We learned that we could actually let the chemically processed blanks dry flat and then rehydrate them later before folding them, which means that they could be processed in bulk and molded by end users. When they get wet, ExCell actuators begin to change shape within seconds. Depending on factors such as whether they're fully submerged and whether they encounter external resistance to their actuation, they reach approximately 80% of their maximum extension in 3 minutes, 90% in 6 minutes, and then they continue to expand for about 2 hours, changing length minimally after that. Unlike the bilayer actuators in Rugeberg and Burgert from 2015, that respond dramatically to changes in relative humidity, ExCell actuators primarily change shape when they're immersed in or coated with water. While we did see minor changes in length when we place them in a high humidity chamber, the effect is negligible compared to their expansion when wet, and we go into why we think that is in the paper. Actuators can be recompressed and dried to reset them, but we imagine that some users would be interested in their autonomous cyclic behavior. We tested 3 actuators for 4-fold hydration and dehydration cycles and measured their overall length after each cycle. The molded actuators start off around 4.2 millimeters long and expand to an average of 68.3 millimeters in the first hydration cycle, more than 16 times their molded length. After the first drying cycle, they contract to an average of 27.2 millimeters long. With repeated cycles, we can see that while the expanded length increases slightly each cycle, the overall range of shape change is starting to decrease. We would need to do more extensive tests to understand whether the actuators eventually reach a static state or whether they just settle into a range of smaller actuation. The tab and slot connectors make it simple to assemble ExCell units into 1D, 2D, and 3D structures using CA glue. They also provide a convenient attachment point for other materials, as we'll see in the applications. For the purposes of rapid prototyping, dummy actuators can be created by laser cutting paper using the ExCell template and folding them the same way as the wooden actuators. This gives users a mock-up that they can push and pull to get an intuitive sense of how a construction will behave as it expands. We envision ExCell being used in a range of applications from interactive pop-up art to environmental interventions, and we present 4 examples in the paper. These include an animated diorama showing fungi fruiting after rain, an indicator that lets users on the ground know when a rain gutter is clogged and needs to be unclogged, a deployable shelter for marine life, which could be used out in the wild or in aquaria, and expanding booms for clearing spaces in ponds suffering from duckweed overgrowth, which would allow for light and gas to be exchanged. Thanks so much for watching our presentation, and please see our paper for more details about ExCell.